We need it. So the ball of radius r centered at x naught is x and v such that the norm of x minus x naught is less than r. Now, given our discussion over there, what does this really mean geometrically? Right? So this is the collection of points that are at most distant, or that are less than distance r from x naught. This is the open ball of radius r centered at x naught. Open ball, radius r, centered at x naught. Now, Samuel asked me before I noticed, let r be real number, r positive. Haha, beat you to it. Let's see here. Sorry, small victory. You can also talk about a closed ball centered at x naught with radius r. And what would that be? If you don't mind, I'm going to use some color coding to do that one. So the open ball has like a fuzzy edge, whereas the closed ball doesn't. It's got a closed edge, right? So here's the closed balls of radius 1 in the plane that we were just talking about over there. Maybe you shouldn't sign up for this. Maybe you shouldn't sign up for yeah. Oh, hey, wait a minute. I haven't given you permission to be here. I said for the hour. I didn't say more. Wait a minute, is it only been an hour? Yeah. Oh, okay. Hey, you got 4 extra minutes. It's here. It's fine. Thank you for attending. Anytime. So this would be the closed ball in the what? In the taxicab norm, right? Closed ball radius 1 taxicab norm. Closed ball radius 1 soup norm. Right? Closed ball Euclidean norm. Right? If you want to make them open, sorry, this gives me joy. La 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 la. Okay, anyway. All right. So there you go. These are open ball and closed ball. Now, furthermore, if x naught, right, is an element of U and there exists a positive radius r greater than 0 for which the ball of radius r centered at x naught is a subset of U, all right, then we say what? It's what's called an interior point. Of U. All right. If each point in U is an interior point, then we say U is an open set. All right. So as a kind of silly example, open balls themselves are open sets, because if you think about any point within an open ball, you can think about another open ball within the open ball around that point, right? Now I would ask you a question. I mean, we can think about Rn. N equals to 1, what's an open ball? Right. Just an open interval. Yeah. N equals 2, an open ball is it's an open disk. Right. N equals 3, it's an honest to goodness open ball. Right? It's like one of those fuzzy Nerf things, you know. It's solid, but not the edge, so to speak. I mean, all right. You can also talk about a deleted open ball. A deleted open ball is an open ball where you just remove the center. All right? Those are important to limits. You can talk about a boundary point. What's a boundary point to a set? If this is my set, right? If this is a boundary point, what's that mean? It means any open ball you take, right, any open ball around that point, if it's a boundary point, there's points both inside and outside the set. Yeah. That's a boundary point. Yeah. You can talk about an isolated point. What's an isolated point? A point is an isolated point of a set if there exists some radius which, when you're at that radius or smaller, there's no points in that open ball except for that isolated point. It's just what it sounds like, right? So like an isolated point is, it's like out here, right? Because although when I take this open ball, I got points in here, right? When I take any of these, I just get that one point there. All right, isolated point.
So we're looking at the reals, and U is the set of rational numbers, then none of them would be isolated points, even though we're not including all of them.
That is true. Every rational point is not an isolated point in the reals, yeah. The rationals are what are called dense in the reals. But now we are starting a discussion which properly belongs in Math 431, which, just a check I cannot cash in here. So, I mean, there are things I will say, but okay. All right. So, the point I wanted to make with you guys here, and why I'm jumping a little bit around in the notes, is because I think it's good to have this discussion together all in terms of one story arc. So if you start thinking about the plane, right, it's a good example to understand topology, just basic topology. All right, what we're talking about is really metric topology, because it's topology which is born of a distance function. All right, so this is called metric topology. So my question to you would be, if you think about an open set in the plane, right, is it going to matter if we view whether it's open with respect to the Euclidean norm, or is it open with respect to the p equals 1, the taxicab norm, or is it open with respect to the p norm for other p, or is it open with respect to the max norm? Do these different norms give you different concepts of what an open set is in the plane? It turns out in infinite dimension, these do give you different notions of open set. I don't have an example. Well, I'll give you one. I made a copy of the 10th chapter in Zorich. I will post it for you guys. Zorich is a substantial book. But no, it doesn't matter. You can, because the thing is, you can see it right here, right? Clearly, if you can put an open ball, open disk around a point, you can inscribe an open diamond about that same point, right? And it's not hard to see that you can easily inscribe other shapes inside these, right? Like I can fit a circle down in here, right? And I can put a square inside that circle, and I can put a diamond inside that square. And if you draw enough of these, you've got all the inclusions you need to see that whenever you've got an open disk, square, diamond, you've always got an open disk, square, diamond below it, right? So you can always shrink down and get an open ball of the next norm at any point.
This looks like
What's that?
This looks like alchemy.
Looks like what? Alchemy? But anyway, my point to you is actually it doesn't matter from a topological perspective which norm we use. All right? They all produce the same topology. And in fact, they all produce the same limit. Because the concept of limit is actually a topological concept. And I could tell you a function is continuous from a norm space to a norm space if the inverse image of open sets is open. And because the idea of an open set actually is independent of the choice of norm, that's some evidence that the concept of limit is also detached from the concept of norm. This is important actually because one of the theorems I want to prove for you guys is if we have a function that goes from a vector space to a vector space, then if I take the limit of a vector valued function, you can do it like component wise. So if I have, like f of x is equal to f1 of x, comma f2 of x, comma f3 of x, that's, I should really say like f1 of x times w1 plus f2 of x times w2 plus f3 of x times w3, where w1, w2, w3 are the basis of the range. Well then that limit will exist if and only if the component functions f1, f2, f3 separately exist limit to something, and then the limit is the corresponding sum of those things. It turns out that there's something dastardly in the proof that requires me to assume a particular property for the basis. This freedom of using any norm I want allows me to pick the norm I like, to construct the basis that I so choose, and it just gets me around a kink. Otherwise, I'd only have the theorem for sort of, they're not really orthonormal bases, but they're bases with a particular property. The property is this. And it seems like a natural property. If I have the norm of, say, x1 v1 plus x2 v2 plus plus xn vn, right? Well, that should be greater than or equal to the absolute value of any particular component. Here v1 through vn is the basis, right? So it seems like this, how could that not happen, right? This is certainly true for the standard basis. All the standard bases I've listed have this property. But you can imagine other bases where this is not the case. You can do something conniving where the basis is something like this. So they're not collinear, but they're just kind of, and then if you do like, I have an example in the notes where, let me just tell you it. Actually, let me show it to you. You're like, you got so far without using the projector. I know I did, didn't I? But at some point I have to face facts. I tell you what, would you like me to go all of today without using the projector? I could do that. Don't matter. I'm tired. I'm going to use the projector. I should be allowed. Should have brought these glasses for something. All right, so we'll start at 4:20, and so we'll end at 5:50, hopefully Friday. As long as a NASCAR driver doesn't come in.
So is there a particular reason we're doing an hour and a half rather than an hour and 15 minutes every day?
Yes. It's because I can't condense my thoughts down, mostly. Let's see here. Where was I? Oh, yeah. Where'd it go? Come on. What's the advanced calculus, right? Yeah. All right, I'll remember eventually. In Calculus 1, I try to get past the limits as fast as I can, and I'm trying to do the same in here, but obviously I love linear algebra too much, and I said far too much about it. All right. So here is, let me kill off these lights. Come on. See if my laser still works. So how many here have had Calculus 1 with epsilon deltas? Who has not had epsilon deltas in Calculus 1? Oh no. In high school. Well, good news. This will give you this will give you a chance to learn that, because technically it's a special case of this. So yeah. Sorry. It's not that bad. It's not. All right, so if we have a function which goes from one normed linear space to another, all right, and this domain of f could be a subset of V, right? It doesn't have to be all of V, right? And if x naught is either a limit point, which just means that there's a neighborhood around the point which exists in the domain of the function, right? Well, it doesn't mean that. It means that there's a deleted ball inside the domain of the function. It could be that we want to allow limits of functions. We want to take limits at points where the expression we're limiting is not defined, right? That's where the interesting stuff happens in calculus. It's still true here. So to say it's a limit point is not to say that the point's in the domain of the function. It's to say that points near that point are in the domain of the function. Okay, with nearness measured by this abstract norm we're talking about here. Then we say that the limit of f of x is equal to L if and only if for each epsilon greater than 0, there exists a delta greater than 0, such that if x is in V and it's within delta units of x naught, then the output f of, oh man, that's supposed to be L. Son of a gun. That is an L. Shnikes. L. L, yes, exactly. Then if L is equal to f of x0, we say that f is the continuous function at x naught. I'm sorry, I have butchered this definition. I'll fix it though. Anyway, is that unclear enough? Yeah. Yeah, not really. I don't want to say the domain has to be open.
So what if we're trying to take a limit at a boundary point?
Well, I think at a boundary point, I think a boundary point would still be a limit point. I may not have addressed that case. I'd have to think about that, guys. I know that this makes sense. This certainly makes sense for an open set. I might need further terminology to deal with boundary points. Let me, that's a good question. Let me stick it in my list of things to feel guilty about. So some easy examples. If you have an affine function, right? Like if we have f of x is cx plus b, where c is a real constant and b naught's a fixed vector in w. So, well, fixed vector in v rather. Then we can calculate the limit as x goes to a. What I'll do is I'll pick delta. I'll assume c is not 0, so I can put delta as epsilon over c. I look at the difference between f of x and f of a, which is cx plus b naught minus ax plus b naught. That gives me the norm of c times x minus a, but by properties of norm, that factors out the absolute value of c, x minus a, but I chose delta to be less than epsilon over norm c, so this gives me epsilon. Bam. This is continuous. So f of x, scalar multiple plus a constant vector, continuous function. Who would thunk it? Everywhere. Because this works for arbitrary x naught. So this tells us, among other things, that the identity function is continuous, and also that translations, in other words, well, almost the same argument works for c equals to 0, which will give you, if you just add, if a constant map, it's also continuous. So another example, if you have well, here, just the next example is actually just fix a constant. You can prove that the limit of a constant map is the constant. It's a pretty simple epsilon delta. You can make delta equal to 3. Because when you take the f of x minus f of x naught, you just get w naught minus w naught, which is 0. 0 is less than epsilon independent of x, so yeah. Whoop-de-doo. Now, example 1.3.6 is a non-example. This one actually doesn't exist because, okay, so like in one dimension, this would be x minus a over absolute value of x minus a. That's going to 1 from one side and minus 1 from the other. It's actually the algebraic thing you can use to build step functions. It's a formula for step functions if you just tinker with it a little bit. But even in one dimension, you can see that the limit at a doesn't exist, right? Because the left limit's 1, and left limit's -1, and the right limit's 1, right? It gets so much worse when you have more directions because it just, you can make, I don't know what, you can do lots of things. It's bad. It goes to any unit vector. I think it approaches all possible unit vectors depending on different polar approach. It doesn't exist. This is not a proof it doesn't exist. This is just an argument by geometry that it doesn't exist, all right? So, yeah. I guess I could make a very nasty homework problem, prove this limit doesn't exist. Now, on the other hand, if I look at this, g of x is norm of x minus a over norm of x minus a times x minus a, well, that probably does have, I think that does have a limit, and it's clearly 0. Now, I haven't proved that, but I believe you could prove. I'm just trying to give you an example. Now, this would have the continuous extension of like g tilde. See, basically that just puts a hole in the graph. Actually, a lot of holes. Well, just one hole? Just one hole. Just one hole. I'm not sure what the point of this example is. I'm just messing around, okay? Proposition 1.37 is interesting. F of x equals to norm of x. Hey, guess what? That's a continuous function. So the norm is continuous. Yay. Here's the argument. F of x minus f of a is the absolute value of norm x minus norm a. And what did I do? I pointed out that if I have 0 less than that, less than delta, I can add 0, use the triangle inequality, and get that the norm of x has to be less than or equal to delta plus norm a. Then I use that down here to replace that with that. There it is, right. I mean, this would take me 5 minutes to work out. If you didn't follow it, it's cool. It's there for you to look at. All right, let me get to the interesting stuff. Guess what? Limit laws. They're true. So the limit of a sum is the sum of the limits. You can pull constants out just the same. And if you have two continuous functions, their sum and their scalar multiple are also continuous. The proof is just identical to what you saw in Calculus 1. I say that assuming you took me or Sperano. I don't know if the other Calculus 1 instructors have our same will of fire. Let's see here. But basically the proof is just you have these two limits exist. That gives you control over this difference and that difference in terms of their size. So you pick a delta 1 to make this less than epsilon 2. You pick a delta 2 to make that less than epsilon over 2. You pick the minimum of both of those delta. It gives you control over both. Use a triangle inequality. And then since this is less than epsilon over 2 and this less than epsilon over 2, this less than epsilon. So that's some rule. It's the same argument I give in Calculus 1. Just instead of norms, I have absolute value in norm 1, in Calculus 1. And the scalar multiple argument is very similar to the one I already talked about today. Now, when I was writing up the notes a couple weeks ago, all of a sudden I ran into a snag in the next theorem and I realized I needed this result. I didn't realize I needed to in previous years, but this is something I need in order to proceed here. So constant vectors pull out of the limit. If I have the limit of f of x is L, where f is a mapping from a normal linear space to the reals. All right, so f is a real valued function. Then if I have a real valued function times a fixed vector w naught, then the limit of this is just the limit of the function times w naught. Very natural result. The proof down here is quite straightforward. I pick a delta such that I get the norm of f of x minus L is less than epsilon over the length of w naught. I can do that because I'm given the f it has a limit which exists, right? And I'm assuming that w naught is non-zero, I think, because if it's 0, it's obviously true. So with that delta in mind, norm, factor the w naught out, use properties of norms to pull out the absolute value of f of x minus L, but then this is less than epsilon over norm w naught, which gives me epsilon again. All right. So consequently, we can pull constant vectors out of the limit of a function times a constant vector. Okay, not You're like, well, so? Fine, you got me. So that brings us to our next concept. If we have W and V are normed linear spaces, if I have F from V to W, if I have a basis for W, which is W1 through Wm, then I can find component functions of F. These are real valued functions from V to, so they go from V to the reals. So basically I can write the function as a linear combination of these component functions against the basis of W. These are the component functions, like in calculus 3, we have a parameterization of a surface or something, right? We have like x of uv, y of uv, z of uv, those are component functions, all right? But there's no expectation of linearity. Actually, there's no expectation of linearity here either, because this is not a linear function on the normed linear space. It's just a function on normed linear space. Anyway, these are called the component functions of F with respect to the gamma basis. All right. So the next couple pages I devote to proving things about component functions. The first theorem I prove, I should definitely talk about right now because it's very much related to everything we just said, is that if we have a basis W1 through Wn and we have component functions, then if you know that the limit of each component function is L sub I, then guess what? The limit of the whole function is just the linear combination of the limits of, it's the limit weighted linear combination of the limit. I mean, it's the natural thing. I don't know how to say it, but it's this. And the proof is really quite simple. First of all, to say f of x has component functions is to say that you can write it as a sum of real valued functions against a basis. But then by linearity of the limit, by the way, if we can prove it for 2, we can usually use induction to extend to n, all right? You're like, you never actually do that. That's true, but you guys could actually do that. You don't need to see me do it. Maybe I should make it homework. Let's see here. So we can pull the sum out because linearity is the limit's additive. Then this lemma that I can pull a constant vector out, the basis is fixed, right? Independent of the limit, so I can pull the basis vectors out like that. These are given to be L sub I, and there's the theorem. So what this says is that if you can calculate the limits of each component functions of a vector valued function, then the limit of the whole vector valued function is just the linear combination of those limits in the natural way. So next time I'll pick up this story with trying to do the opposite direction, which is to say that if I know that the limit exists, then each of the component functions' limits must also exist. Strangely, that's actually a little bit more technical. So ultimately, we're building to the following statement. Basically, whenever you take a nice function of coordinates on a normed linear space, you get a continuous function. So it's just like calculus 1. Anything that you have a nice formula for is continuous, right? Any place where you have division by 0 or other things, well, then you got to be careful. It's the same for functions of normed linear spaces. And so once we're done with that, we can define derivatives, because derivatives, again, are defined in terms of limits on a normed linear space. So we should be there next class. I don't have much more of this. I will use the projector as to not drag this out. This is really not where the course is long term. It's just, this is necessary. Just like limits are necessary for calculus 1, but calculus 1 doesn't stay with limits, right? This is kind of that part of this course. So sorry if it seems, I mean, it should seem foreign to you, parts of it. More importantly, mission 1 is out, so you can start working on it and ask me questions. I have office hours. I welcome them. Your questions. Not my office hours. Actually, I hate office hours. I don't hate the idea of office hours. I hate having to schedule office hours. Does that make sense? Like, I want students to just come find me whenever I'm like free. Just give you your phone number? Nathan Bedell called me in a faculty senate meeting like last week. That was the best part of my meeting. I actually like it a lot when students call me in meetings. It's pretty awesome. My dream is to call students back during their meetings, but you guys always put it on silent. You know, fun. And you're texting. You and your texting. So annoying. Like, I can call students all day long. Nothing. I text them. Immediate response. Why even have a phone? Why not have like a texting machine or something, you know? Oh. Did I show you guys my, did I show you, did I have this